Okay, so I will present some work that we did recently with Adrien Notar-Antonio, who's here, a postdoc in Paris, on the three-state parts model on planar maps. And to tell the truth, this work is a bit technical, say, well-conducted computer algebra, and the ideas would be a bit hard to convey, a bit unpleasant to listen to. And so instead of that, I've decided that I would tell you the whole story that covers a few decades in a certain sense. I'll start with the usual definitions, even if you don't need them. So a map, a planar map, is a connected planar multigraph, which means that you allow loops and multiple edges, and which is given with one of its proper embeddings in the plane. And all this is taken up to continuous deformation. So in a map, you have vertices, which have certain degrees, like here 5, because the loop counts twice. You have obviously edges, and you also have faces, which have themselves a certain degree, which is the length of the boundary, here 3. And since I want to count maps, I will systematically root them by choosing a certain corner, so between two adjacent half edges. And this defines automatically, well, a root edge, a root vertex, and the root face, which I will always take as the infinite face, the unbounded face. Its degree I will call the outer degree for obvious reasons. Now I will often consider subfamilies of maps, of planar maps. All my maps are planar, namely triangulations, in which all faces have degree 3, including the outer face, as you can see here. So that's my outer face. And if I relax the condition on the outer face, I will call near triangulations the resulting maps. So here's a near triangulation with outer degree 1, 2, 3, 4, 5. One important construction when you play with maps is duality. So if you start from a map M, what you will do is to create a new vertex in red, it's not so clear, in every face of M, and then you join two vertices that are on both sides of the same edge, like here. So here's what you obtain on the map in red. This is the dual map, M star. And if you start, as I did here, with, say, a triangulation, every face has degree 3. As a result, in the dual, every vertex has degree 3, and this is what we call a cubic map. And if you happen to relax the condition here so that the root face has any degree, so you have a near triangulation, on the other side, you'll get a near cubic map, meaning that the root vertex is allowed to have any degree. Finally, my maps will be colored, and always vertex colored. I don't color faces. So this means that I'm given a set of Q colors, here 4, and I assign a color to every vertex. So if you have n vertices, there's Q to the n coloring. That's not so hard to count. But what's harder to count are proper colorings, those in which you forbid such monochromatic edges. That is, you want neighbor vertices to get systematically different colors. And the parts model is, in fact, a generalization of this counting problem. Our favorite tools, my favorite tools, are generating functions. So if you have a class of maps C equipped with a certain size, say the edge number, the associated generating function is a formal power series in one variable t. So this t will systematically be my size variable, and every map of the class contributes a monomial t to the edge number. And of course, you can imagine that if you record several statistics on map, you will get generating functions in several variables. And the most important definition here is the definition of algebraic series. So this series C is algebraic of degree k if it solves a polynomial equation, P is a polynomial, of degree k in its first variable. We'll see many examples later. So this being said, I will now present an old result, conjecture, 15 years old or so, and a new result. First, the old result is due to Tat, who else, who proved that if you look at triangulations, the colors are not so good here, and they are properly three-colored, so that's the class of triangulations that we saw this morning at least 3 times, if I'm not mistaken. Then the generating function of these maps, counted, say, by vertices, is algebraic of degree 2. So that's its minimal polynomial. So that's the old result. Now the conjecture asks similar problem, properly 3 colorings, but of the dual class, that is the cubic maps. And for this problem, Bruno Salvi came some 15 or 16 years ago with a conjecture saying that, well, apparently from the first few coefficients, it seemed that the generating function of this properly 3-colored, so it's not exactly cubic maps he looked at, but near cubic maps. So you have all vertices of degree 3 except from the root vertex, which has degree 1. And he conjectured that this series was also algebraic, but of degree 11. And this is the nice minimal polynomial that he could guess. So it has degree 11, of course, in C, in the series, but also in the variable, I think. And the new result, well, is that this conjecture holds true, and that's what we proved with Adrien. And in addition to this horrendous equation that you've seen, we produced, I don't like this mouse. We produced a simpler equation for the derivative of this series. So here it is. And now its degree in T is 2. And in a certain sense, that's optimal. That's the best you can do. And in fact, this result is a special case of what we actually did, because what we proved is that the same result, that is algebraicity of degree 11, holds for a more general problem where now you count all 3 colored cubic maps, but you put a weight on the bad edges, the ones that are monochromatic. This weight is nu. So when nu is 0, you are just not counting anything that would have a non-proper coloring, and you're back to this problem. But so this is obviously more general, but we get also something algebraic of degree 11. And this is the so-called 3-state parts model, which I'm going to discuss in the next slides. So let me start from a definition. So you take a positive integer q, that will be your number of colors, a map M, what I call, for short, the Potts polynomial of M. In fact, the partition function of the q-state parts model on M is the following polynomial, which counts. So this is a coloring of the vertices in q colors. And you have this weight, nu, per monochromatic edge. So this is the number of monochromatic edges. We can take an example. So if your map is this little segment, well, if you want this edge to be monochromatic, giving a weight nu, well, you have q ways of doing that. You choose the color of the root vertex. But if you want it to be bichromatic, you have q choices for the first color and q minus 1 for the second. So that's the Potts polynomial of this map. And in general, it's not hard to see that it's always a polynomial in q and u. And there's this interesting duality relation, which holds only in the planar case, which tells you that the Potts polynomial of M and of its dual are related. But you see the value of q is the same, but the value of nu, which records monochromatic edges, is different. And the relation between nu and nu star is this one. Okay, so now that we know what this is, we can define for a class of maps, say near triangulations, we can define its Potts generating function. So it's a series, so in one main variable t that will record the size, and here I take the vertex number. There's an additional variable y that records the degree of the root face, the outer face, which may not have degree 3 since we just have near triangulations. And here you have this Potts polynomial. You can see this just as a counting problem, so where you would sum over all near triangulations and vertex colorings. And then, so in addition, you have this weight new to the number of monochromatic edges. So we can look at small maps, small near triangulations. So with one vertex, this is the only near triangulation with one vertex. It has outer degree 0, one vertex, and q colorings. So this gives this, this monomial here. With 2 vertices, you have exactly 2 near triangulations, depending on whether you put or not this loop. And this will give this coefficient here, times t squared, and so on. So you have to think of this series t of y, which is really my main character here, as a power series in t, whose coefficients are polynomials in q, nu, and y. Of course, we can do the same for the dual class, the near cubic maps, except that now, so what was the vertex number becomes the face number, and the degree of the root face is replaced by the degree of the root vertex. Okay. Now, given what I told about duality, computing this series, or that one, that's completely equivalent using this relation. Now, if you just want not the full Potts model, but just proper colorings, so here you will specialize this nu to 0 to kill monochromatic edges. And here you would specialize to nu star equals 0. And nu star equals 0 means that nu is 1 minus q. So you see this is obviously not the same specialization. And this is one way to explain that at the level of proper colorings, these two classes are very different. And this was old result, Tutt's result, and Bruno's conjecture. Okay, so I come back to our result. What we proved is that if you fix the degree of the outer face in your near triangulation, you say it's I, then for any I, the generating function ti, counting these, the 3 Potts polynomial for all near triangulations of outer degree I, it's algebraic of degree 11. And the smallest equation that we found in this class of problems is the one again for derivative. So for the derivative of t1, we found an equation that has only degree 2 in little t. And if you want the whole thing, the full series with the outer degree, you jump to degree 55. Okay, so now I want to spend a bit of time. I will return to the initial problems with just proper colorings, not Potts. And for the easy class, triangulations, and for the harder class, cubic maps. And I will just try to compare them. So what do these two results have in common? Well, algebraicity. It's easy to say. And also the universality class. That is, in terms of asymptotic counting, in both classes, the number of colored maps behaves like some mu to the n to the minus 5 halves, which is the usual asymptotic behavior for uncolored planar maps. Mu is 8 in the first case, and the solution of this lovely polynomial of degree 9 in the case of cubic maps. And at the moment, I would say that this is everything that these two problems have in common. So instead, I will discuss how they differ. So they differ in several ways. First, in terms of genus. If you look at the, what did I do? If you look at the minimal polynomial of this series here for triangulations, you have a curve of genus 0, while here you have an elliptic curve. They differ a lot in terms of combinatorics, because in this case, we have a lot of combinatorics explaining whatever we want. And for a start, we have a bijection with bipartite maps, two colored maps, which was already known to Tut. And it goes as follows. So we saw it this morning, I think. You start from your favorite three-colored triangulation, and you will delete one vertices of one color, so the purple ones. And so there's two colors left. What you have is a bipartite map. And to go backwards, you put one of these purple vertices that we deleted inside every face, and you triangulate every face, and you're back. So these two counting problems are the same. And then come much more subtle and richer bijections, which transform these maps into families of trees. So we've heard about this paper several times this morning. I'm glad it played such a role in your work. And so when you have bijections with trees, this allows you many things, but in particular, it explains combinatorially why you have algebraic series. Because these trees, they have a certain branching structure that is reflected at once by generating functions. So I won't say anything more about that, but that's very important. And on this side, we have just nothing like that. Another difference is that here, if you take a triangulation and want to three-color it, so you choose the color of the root vertex, the color of the other vertex at the root, at the other end of the root edge, and then every triangle must contain exactly one copy of each of the three colors. And so you just have one way at most to propagate this coloring. And so this means that every triangulation has between 0 and 6 colorings. Whereas here, from our asymptotics, we can conclude that in this case, every cubic map has an exponential number of colorings. So this is not really a coloring problem, in a sense. And finally, in my point of view, I would say that one main difference between these two problems, between the natures of these two problems, is that this one is what I call one catalytic, and the other is two catalytic. So this does not refer to subtle chemistry, but to equations, of course. So let me tell you what I mean by this one and two catalytic thing is. So I claim that the first problem, properly three-color triangulations, this is one catalytic. What do I mean by that? Well, I mean that there is a way to approach this counting problem which involves adding one additional statistic. So I will get into some details. So we've seen already that this counting problem is equivalent to counting bipartite maps, so with vertices colored in two colors, by edges. So we have a series B, depending on a size variable T. And we're going to approach this problem, as Tut did in the good old days, by trying to see what happens when you delete the root edge. So let's do that. Let's delete this edge. So there's two situations. Either you get two pieces or a single one. If you get two pieces in the first case, you know how to go backwards. You just create an edge between the two root vertices. But if you end up with this little blue bin here, there's some ambiguity. You don't know what you started from. And the reason for that is that the edge that we have deleted, it It was starting from this corner here, but maybe it was ending here, this white vertex, or at this one, or at that one, and so on. So there's several maps of size n that give the same map of size n minus 1. And so this construction, this property tells you that if you want to use it to count your maps, you are somehow forced to add this additional statistic, which is precisely the number of white corners in the outer face. And that's also half the outer degree. So, okay, so we will do that. We will consider this additional statistic, which is sometimes called catalytic, and the corresponding new variable, say y, which will be also called catalytic. And then if you sit down for some time, you will end up writing for series B that now involves the size variable t, but also this additional variable for the outer face. You will end up writing this equation, which is really typical of what you get when you count maps. So with here a divided difference. And this is a typical equation in one catalytic variable. So in general, you may think of them as you have some polynomial that relates one bivariate series, b of ty, and one, or in fact several, as we will see, series that depend only on t, on the size variable. So that's for the first problem. I claim that the second is, or at least for the moment, too catalytic, which means that I cannot write an equation if I'm not allowed to add two additional statistics. And if I agree to do so, I can even address much more general problems, like the full Potts model on these cubic maps. So that's not just proper colorings, but the full Potts thingy with the new. I can replace the number of colors 3 by any q. This is completely equivalent to the dual problem, so the q Potts on triangulations. With the same ideas, one can do q Potts on general planar maps without restrictions on the phase degrees. And it's not hard to give a little taste of the reason why two more variables are needed. And I would say that the reason for that is that if you want to compute the Potts polynomial of m in a recursive fashion, well, you can do it, but then you have to involve the Potts polynomials of two maps. One is obtained by deleting the root edge e, and the other is obtained by the dual contraction of the root edge. So this is deleting the root edge of the dual, in a sense. And so these are the two constructions, and we've seen with the previous example that when we were just deleting the root edge, so that was the top picture, we had to consider the degree of the outer face. And here we are led to consider also the dual parameter, which is the degree of the root vertex. Okay, so this is a bit hand waving, but I think this is really the idea. So using these ideas, one can write a number of two catalytic equations for q Potts models. And so here's one that we wrote with Olivier Bernardi some 15 years ago. So you don't have to look at the details, just at the general form. So we have this series q that depends on t, q, nu, but also these two catalytic variables, x and y. And q is 1 plus t times something. And in this something, you find, of course, the original series, but also two series here that do not depend on y. And so they are the coefficients of y to the I in the main series. And also here, a series that does not depend on x. Okay, so at the moment this is just an equation, and the connection to our problem is that when you specialize x to 0, this is the pots, the Q pots generating function of near triangulations. Okay, so we had an equation. Here it is in short form. This was not the main result of this paper. The main result was that for certain values of Q, of the number of colors, but which you can specialize to any real number. So when Q is of this very specific form, 4 times the square of the cosine of a rational multiple of pi, then you can derive from this beast here an equation in only one catalytic variable for the series that we like. And this includes in particular the Ising model, when you have 2 states, 2 colors, and the 3-state Potts model. And so we did the thing explicitly, bravely. So we started from the top equation and derived an equation in just one of these catalytic variables. So I will show it to you. So again, this only works when Q is 3. And then we have an explicit polynomial, Pol, in the main series for 3 pots on near triangulations and 4 series that do not depend on y, which are coefficients in the original series. And this polynomial vanishes. So I have even started to write the first terms. It's not very charming, so has degree 5. In ty cubed, you start having here in the coefficient the first of this series that does not depend on y, and so on and so forth. Needless to say, in contrast with the previous case, we have no combinatorial explanation at all, direct, I mean, of this equation. But still, we have one equation with one catalytic variable. So now you may wonder, okay, yes? Yes, it is explicit. This equation is explicit. It gets bigger when m gets bigger. Okay, so you may say, okay, 1 catalytic, 2 catalytic, who cares, what's the difference? There's one very important difference, namely 1 catalytic series, they are always algebraic. So that's a deep theorem in algebra that is due to Popescu a long time ago. And here is a statement. So imagine you have not one equation, but maybe a system of equations that relate j plus k unknown series. So the first j depend on t and y, but the last k, they depend on t only. So this time I'm writing the variable t explicitly. And you assume that if you force the solution to consist of formal power series, and you want the k last series to be independent of y, you assume that you have a unique solution to this system with these conditions. Then automatically all these series are algebraic. So I have been ignorant of this result for years and years, to the point that 20 years later, with Arnaud Géhan, we proved the same result for a single equation. Not very impressive, of a proper type, which is something that guarantees uniqueness of the solution. But so first I understand the proof in this paper, which is not the case up there. And in addition to that, we have an effective elementary procedure to come with minimal polynomials for all these series. And recently, Adrien Notarantonio and Sergei Yurkevich, they came with an extension of our approach to systems. So getting back to the original result. Okay, so now we can put things together. So we take 3 parts on near triangulations. We know that we have one of these 1 catalytic equations we know that one catalytic implies algebraic, and so we reach the point where we were 15 years ago, that we know that this series, this three-part series, is algebraic. But what we were completely unable to do at the time is to make this explicit, because things were just too big. And so we had no minimal polynomial for even T1. So since then, Adrien and his collaborators, they designed much better algorithms than what we had in the first paper, but still, this equation was too big and resisted. So it remained a challenge for some time, and so now I'm telling you that we have a solution, and in the next few slides, I want to tell you about what we actually did with Adrien, so what happened. What changed the situation? So, first of all, I want to tell you some thing about the general approach, what we did with Arnaud Géal, to these equations. So imagine you have one instance, so a polynomial in this series S in T and Y, and K, here I took 4 auxiliary series, that depend on T only, of a proper type, whatever this means. Then one of our results tells you the following. So you have this polynomial here in 7 variables. You take the discriminant of this polynomial with respect to the first variable. So this gives you a polynomial delta in just 5 variables. Okay, why not? You evaluate this delta at the unknown series. I mean, we don't know how to do this explicitly. These series are unknown, but still this object exists. And it is now a polynomial in Y whose coefficients are formal power series, unknown formal power series. And one thing that you know is that if here you have 4 unknown series, then this polynomial in Y will have 4 double roots. So it will constrain its coefficients. That is, it will constrain the series AI. So more precisely, starting from this, we can now write that for each of these series Yi, well, delta is 0. The derivative of delta is 0. So we have 8 equations here in 8 unknowns, the Yi's and the AI's. And if you add that the Yi's are distinct, you have some hope that this system has dimension 0, and hence that every AI, say, will be also algebraic. So all these arguments, they start from a one catalytic equation and produce a polynomial system, hopefully of dimension 0. So we can specialize this to our pots problem. So we get back to 3 pots on near triangulations, for which we had an equation of this type. And we get indeed a certain discriminant, delta, which involves these 4 unknown series, has degree 26 in Y, and 10 in these unknown series Ti. So that's big. And this is why the problem resisted. So here's again the situation. In addition to that, when you would expect 4 double roots, or at least 4 double roots in Y by the theorem, in fact, it's not hard to see that you have 10, and I guess you have 7, sorry, and I guess this is related to this 7. And in practice, there seems to be even 10 of these double roots. So there's something with this problem that is big, but that maybe doesn't need to be so big. Since you have so many double roots, I mean, you have too much information in a sense. But we were playing with that on and on with Adrien, and suddenly I remembered something that we have in our second paper with Olivier Bernardi on maps, which is a statement of this type, but with smaller objects. And so here it is. So in that paper, we proved that we have not one, but two polynomials, say d plus and d minus, which we evaluate at these unknown series, and that depend on some variable that is now u rather than y. And as polynomials in U, they have degrees 5 and 6. Polynomials in the TIs, they have degree 2, so that's really much smaller. And each of these has two double roots. So that's a condition of the same nature. It gives again 8 polynomial equations. D plus and its derivative vanishes at U1 and U2. Same for D minus. So we have again a system of 8 equations, but it is much smaller. And we were able to work from this one, and in fact, by taking resultants rather than Grabner bases for some reasons, we were able to reach a minimal polynomial for each of the series Ti. So that's somehow a summary. I think that was one key point. There are others that would take some more slides. I just want to mention one of them, which was new for me, namely, so we are using Maple. And so Maple is able to compute effectively elliptic parameterizations of curves of genus 1. And we used that a lot to factor our equations. If you are greedy about this kind of details, I can give more, but some other time. Okay, so anyway, with that, we ended up solving the three-state parts model on near triangulations. Now we were encouraged by this happy success, and there was a second problem of the same nature that had been around also for 16 years with no conjecture in this case. It was the same problem, but for general planar maps, no constraint on the vertices or faces. And for this one, we obtained, using the same starting point, but an alternative technique, we were able to prove that this series here satisfies an algebraic equation of degree 22, and the genus seems to be 4. Okay. So I want to say a few words about asymptotic aspects of our results. So I get back to the series T1, counting near triangulations with an outer face of degree 1. And now I consider this nu, which weights monochromatic edges, as a positive parameter. So now I have a formal power series in T, depending on this parameter. And I can look at its radius of convergence and look for phase transitions. And so this radius, rho nu, happens to be an algebraic function of nu of degree 5 before the critical point, which is this value, and degree 9 afterwards. So if you look at the roots of the discriminant of the minimal polynomial, as you should, you get a fairly complicated landscape. And what happens for the genus, so the radius, so you start at 1/8, so this is nu. So you start at 1/8, you go down this blue curve until the critical point, and then you embark on this top red curve here. So that's the location of the radius. And in terms of the nature of the singularity, well, we have a critical exponent alpha that is generically 3/2, but 6/5 at the critical point. Okay, and to conclude, where am I? Yeah, that's about it. If I want to qualify with what we've done, I think we've been about as far as one can go at the moment with the explicit solutions of these one catalytic equations. And I would like to mention some tools that I felt were badly missing during this work, and especially during the asymptotic or singular study of the series. And I think these problems, they are recurrent somehow. So the first thing is that we've located the radius, but we cannot exclude that for some values of nu, finitely many, and we know which ones to look at, there could be other singularities on the radius of convergence, which in theory could be visible at the asymptotic level. And we would like, well, either to live with them and compute the corresponding asymptotics, or to rule them out. And Lin Chao Chen has discussed things like that in several papers. I don't yet completely understand what he did, because he has a very strong condition that another dominant singularity should satisfy. And I would like to understand this better. And the second question must be recurrent in models of theoretical physics. So it deals with this critical exponent alpha. So I've told you that, so this is the radius of convergence, that alpha is 3/2 here, 3/2 there, and only changes at the critical point. And my general question is, I mean, how far could we predict that? That is, well, it's easy to compute alpha at 1. And if we could say, oh, given this diagram, alpha has to be, say, continuous in U as long as we don't reach this point. Since for algebraic series, we know that alpha is irrational. So a function that takes rational values and is continuous is constant. So we would not have to prove this 3/2 for every nu on this curve, which is a pain. So I would like a general statement that tells you that under some conditions, the critical exponent is, say, continuous as long as you don't hit some critical point or some intersection of roots of the discriminants. You can add nice assumptions. I think they are needed. But I mean, there's a clear statement that's missing here. I'm not sure it's very easy. And I'll stop here. Thank you. It's not working, but you can play with it.
So you had these particular values of Q for which you
So I missed the beginning of your question.
You had some particular values of Q when Q was 4 cosine
squared
of the rational times pi.
Yeah.
For which there was a change from one catalytic to two catalytic.
Or the other way around, yeah.
So what is your understanding of this? Of these particular values?
I could say accident, but I think that there are several ways of looking at that. First, this phenomenon is not isolated. As I heard, these are the Tut-Behaha values that make this and that model more solvable or whatever. So this is not an isolated phenomenon. On an analytic point of view, I think it has to do with some theta functions becoming algebraic at some points, apparently. So at least the original problem that showed this property was properly Q-colored triangulations, the problem that Stud solved. And so for that, he proved at the end a nonlinear differential equation, which is valid for any Q, any number of colors. And for some values of Q, the solution to this differential equation turns out to be algebraic. And Andrew L.V. Price has a general solution to these differential equations in terms of theta functions. So I think, even though he never wrote that, shame on him, that he should be able to explain this jump from one big class of equations to algebraic equations in terms of special values of theta functions. in physics terms, there's nothing that I understand, but this is generally the case between physics and me.
Well, I mean, the Potts model has a lot to do with representation theory of the temporal Lie algebra, and there is something going on at those particular values in Q as well.
I'm not surprised. I mean, I expect this to exist in several more or less connected worlds.
Also, if I could just add a very small question, this alpha equals 5/6, it must relate to some exponent that...
That's normally the question I ask you. Yeah, I guess it's predictable. I mean, for any Q, there's a conjecture. Or
okay, so if I take it...
okay. And could the value of the critical nu, is it predicted also somewhere or computed somewhere? Maybe in your papers with Gaëtan? No.
There might be some matrix mode, but that would be a question for
Bertrand.
Yeah, there's a question of whether you can do this with matrix models, but I'm not sure. Anyway, if one can do it at all, one will find in the end the same equations. So
Yeah.
maybe we won't be any further.
Yeah, but maybe it exists already, and I should cite that.
Not sure.
It was for your neighbor.
Do you have some examples where the system, the rank of the system is not zero and solved or unsolved cases?
Sorry.
So when you do your systems with multiple roots, you said that you were in happy cases where the rank was zero. Do you have some cases where the rank is not zero?
So the dimension of the system.
Yeah.
Well, no, it would mean, in my opinion, that the problem is ill-posed. Because really this uniqueness assumption that you have a unique solution in power series, it is a strong constraint on what you write. So, I mean, it may be that Adrien has a different answer precisely regarding this example. So you have to talk to him. There's this tricky thing here that in the one catalytic equation, you see, okay, the series in T and Y, and then not the first four coefficients in Y of this series, but the series T1, T3, T5, and T7. And hidden are connections between, say, T4 and T3 and things like that. So there's something a bit weird with this system. And at some point, Adrien was claiming that something, but I don't know why, was not zero dimensional.